Hello students, welcome back. We are done with the reviews. Now, finally, let's begin section 3 of this notebook, and for many students, this is going to be the starting point of lesson 15. Let's discuss Fulmer's method. Fulmer's method is an alternative way to calculate the matrix exponential. So let's begin with a partial review. We used to use the Laplace transform method to calculate the matrix exponential e to the at power. And how did he do it? Calculate Si minus A, which is straightforward. Next, its inverse. And then we have to take the Laplace inversion. Before taking the Laplace inversion, we needed, in general, the decomposition by partial fraction. And that was the computation-intensive step. Let me make a point, and let me take this example here. Let's see. Copy and paste that thing here. Okay, alright, this is what I up to. First, a preparation, Si minus A, easy and straightforward computation. I hope everybody remembers. We went through the very same example before. And the resolvent matrix, it follows from the matrix inversion formula or the inverse matrix formula here. That's for 2 by 2. And then down here we need AD minus BC, which is alternatively called the determinant, and that goes like this. Multiply the principal diagonal, and then the other multiplication, subtraction, and then that's AD minus BC. That's what this is. And then switch the principal diagonals, and then take the negatives. Here's a simplification. Now we have this, so we can decompose by partial fraction, and this is the computation-intensive step. Here in this particular problem, I use computer algebra system to get it done a little bit more easily, but if you don't have computer with you, then this may take some effort because each decomposition by partial fraction is tedious computation, and you have to do it 4 times. But then again, once this is done, the Laplace inversion is not too bad. Coefficient is 2, and then we have the fraction 1 over s minus 1. That'll give me e to the t power times 2. And here, coefficient is negative 1, and then the fraction is 1 over s plus 1, so we have e to the negative t, and so on and so forth. Now, this is complete. Once you take the Laplace inversion, you got the complete computation of the matrix exponential e to the at power. But let's make one further observation here. The denominator is s squared minus 1. They're all s squared minus 1 because they're all coming from this AD minus BC, the determinant, which we call actually the characteristic polynomial. We're going to come back to that issue in a moment. So the common denominator here, so factorization is also common, so the eigenvalues are also common. S equals to negative 1 from this vector, and s equals to positive 1 from that vector. So s equals to negative 1, so e to the negative t, and s equals 1, so e to the positive t. Those are the Eigen functions, and that's common to each component. And then we have appropriate coefficients here. So for each component, we have linear combination with e to the t power and e to the negative t power. So we can separate those for each component. First, 1, 1, and then do the same thing for next component, another entry, and then the last entry, all separated, and that's what we are looking at here. This matrix is given by 2, 2, negative 1, negative 1, all those coefficients for e to the t power. And then this matrix is coming from negative 1, negative 2, positive 1, positive 2, all the coefficients for e to the negative t power. And e to the t power, e to the negative t power, they are scalar functions. So I can always take those out, and what's left is a linear combination of the scalar function e to the t power and e to the negative t power, and the coefficient matrices. See the final form? And now Fulmer's method is starting from this observation. So instead of doing all these computation, start from educated guess like this. We have eigenfunctions, and then coefficient matrices, and then we are trying to identify the coefficient matrices in alternative viewpoint instead of doing these computations. That's Fulmer's method. Now, why are we doing this? Well, for 2x2 case, this computation in step 2 wasn't too bad, because that's primarily because this was okay. Inverse matrix formula for 2x2 matrices, it's easy, 1 over AD minus BC, and switch the principal diagonal. A goes to D, D goes to A, and the other will be just negatives. So we can explicitly calculate the inverse matrix and then simplify. We get the resolvent matrix, and then we can decompose by partial fraction and take the Laplace inversion. But for higher dimension, it's not that simple. This is Kramer's formula for inverse matrix for arbitrary dimension, and this computation is real challenge, especially you are a human. For computers, it's much less of a challenge because this can be done in completely algorithmic fashion, but for humans, this is a challenge. We have a lot of tedious computations. So the purpose here in Fulmer's method is how to avoid this inverse matrix computation. So without calculating the inverse matrix, so without getting all those coefficients, can I still get to the conclusion? That's the idea. So let's come back to this. In this one, Kramer's formula for inverse matrix, the denominator is common, determinant of A, and that's this AD minus BC. And then for this particular matrix Si minus A, it's going to be a polynomial expression of S, and that's common to each entry. So we have common denominator for each of them, and then even if I don't know this part, the coefficient part, we still can see that the denominators are the same, so decomposition is pretty much the same except for unknown coefficient. Same denominator, same eigenvalues, so same Laplace inversion. Excuse me, that was not the right cell. Same Laplace inversion, therefore the same eigenfunctions. Same e to the lambda t, basically. And then about the coefficients, that's unknown, so we can find out later. That's the idea of Fulmer's method. Let me show you that with this same example here. Same preparation, okay? And then let's find out, not the inverse because that's difficult computation, but just this, the denominator only. So the determinant of this resolvent matrix, which we call the characteristic polynomial, and let's calculate that. Same thing, AD minus BC, AD minus BC, crisscross. Simplify, we get same as before, s plus 1, s minus 1. So we have one factor, and then we have another factor, and there are two different factors. So from the first factor, s plus 1, I get one eigenvalue, and from the second vector, I get the second eigenvalue. So first eigenfunction, or eigenvector if you will, second eigenfunction, and then these are going to be common, so you can take those out, factor those out through scalar multiplication, and that too. And what's left will be the matrices, the coefficient matrices. So you can do this rather mechanically. Get the characteristic polynomial without calculating the entire inverse matrix, which is really challenging. Just calculate this AD minus BC part, the denominator part, only this part. The determinant part, which we call the characteristic polynomial. And then get the eigenvalues, and then the eigenfunctions, just by looking up this Laplace table. You see, once you get this characteristic polynomial, after that is precisely the same process we use in Chapter 4. What did you do in Chapter 4? It was not a system, it was just a single equation, but higher order. And arbitrary order, linear, ODE with constant coefficient. We just had characteristic polynomial set up in a little bit different way, of course. And then once you get characteristic equation, you get factorization, and then you get eigenvalues. For each eigenvalue, you can look up those corresponding Laplace inversions and get eigenfunctions from this Laplace table in page 123. Exactly the same process is going on, except that the setup of the characteristic polynomial is a little bit different this time. Deep down they're related, and actually they are the same in the end, but that's not something we're going to discuss it here. Alright, I get m1 eigenfunction plus m2 eigenfunction, alright, and now let's find out m1 and m2. How do we do that? Let's set up a system of linear equations of these two matrices and find out how. Typically, you plug in t equal to 0, so that t equal to 0, so we have, this is 0, so we have e to the 0 power. So this entire thing is identity matrix, I. And this is e to the 0 power, 1 drop out, e to the 0 power, that's 1 also dropping out. That's one equation. Another equation is coming from the derivative and then plug in t equals 0. Take the derivative, by chain rule we get that, a comes out. And then you can plug in t equal to 0, so that's 0, 0 matrix, e to the 0 power, that's I, and that's 1 that drops out, that's 1 that drops out, and so on like that. And if you have higher dimension, it's the same deal. Another derivative, second derivative, and then plug in t equals 0. If necessary, third derivative, fourth derivative, fifth derivative, and plug in t equal to 0, 0, 0, so that you get basically a big system of linear equations of the matrices. Tedious computation, but you can do it because that's elementary algebra, and you can use computers for that. So plug in t equal to 0, we get this. Plug in t equal to 0 to derivatives, we get that. And solving this system, that's not too bad. In this particular case, I simply add them up. Then m1 minus m1 will just disappear. Then we get this. 2m2 is equal to I plus a. So divide by 2, we can determine m2, 1/2 of I plus a. Do your computation. Here's my coefficient matrix. Next, I subtract, then m2 minus m2, that's going to be gone. I'm going to get 2m1 equal to m minus a. Divide by 2. Do your matrix multiplication, the matrix computation, matrix addition and dividing by 2. No matrix multiplication, excuse me. In the end, well, we have the second coefficient matrix. So the conclusion, put everything back into this, and this conclusion we get. And is this the same thing as the one we got before? The answer is, of course, yes. You can easily check those. Where is it? Compare these two. Okay, I ended up switching the order. Otherwise the same, so yes. We just went through Fulmer's method. Which method do you prefer? Personally, I prefer the previous method. It's more straightforward. And then the resolvent matrix computation. This inverse matrix formula works out just fine for 2x2 matrices. And then the decomposition by partial fraction, I know this is pain in the rear end, but then again, it is straightforward computation. And as for pain in the rear end, that's system of linear equations of matrices, that can get pretty bad too. So that's kind of pushed, to tell the truth. Personally, I prefer the former method, but the second method, Fulmer's method, has its own advantage. if I have a matrix of 3 by 3 or higher, like this kind of example down here, then the inverse matrix is gonna be real challenge here. Inverse matrix. It doesn't work like this, and then we may have to do this, and then this is gonna take another humongous computation. So the decomposition by partial fraction is not the most computation intensive step, as a matter of fact. This one is. The inverse matrix part is really the killer, and that's gonna take actually too much effort. For 3 by 3 or higher, it's what can I say? It's really a big pain. So this traditional method, the first method, the straightforward Laplace inversion method, does not work very well. It's not impossible, but if you sit down and try to do it, you'll recognize this is certainly not working. So we're going to be using Fulmer's method for higher order. And then if I go to section 4, there are some higher order problems like this kind of matrix. No, not that. Yeah, that kind of matrix. And how do we get the matrix exponentials of all those? Finding out inverse matrices for those, too complicated. So we're going to end up with Fulmer's method. Okay, so much for Fulmer's methods theory and a motivating example. We're going to talk about the example problems in next videos. Maybe 2 videos, maybe even 3, we'll see.